So we've covered a lot in the last few lectures, mostly about the tangent space. The tangent space at a point P, which is an element of the differentiable manifold. And we identified that as a tangent space at the point P is the set of all of these velocities of these curves gamma at the point P, such that gamma is a function from R to the manifold itself. And the way these velocities, which is what we're calling them, work on functions, where f is an element of the smooth functions on the manifold that take points on the manifold to the real numbers. The way that these velocities operate on functions like this, in order to accomplish this mapping, or I'm sorry, in order to these velocities are maps, right? And the maps will take, I guess I should write that down too. The velocities are maps that take elements from C infinity on M to the real numbers. And the way it accomplishes that is by combining the function with the inverse of the curve operating on the curve's value that gives you the point P, right? So this is ultimately got to be P here. So we know that, for example, it must be that gamma of T0 equals P. And this is how the operation of these velocities is defined. And the set of all of them is the tangent space at a point P. So we've actually made quite a bit of progress there. And we showed that it's a vector space. And then we also showed that its basis, we were going to write its basis vectors based on some chart. And that chart will give rise to basis vectors that can be written in terms of these coordinates, differential operators of the coordinates, which are expected to, when they're used in this way, they're expected to act on functions and then evaluated at P, where we keep the understanding in mind that this object actually refers to this object. F is going to be this blank space here, conjoined with the inverse of, oops, not gamma, I'm using gamma, the inverse of whatever mapping is relevant to the chart, like that, and operating at the point phi of P, like that. So we've got all this down. These are our basis elements of this vector space. So they are the basis vectors, right? If I erase this, and the basis vectors, therefore any arbitrary member, if x is an element of the tangent space at P of x, where this is the normal notation now for the tangent space. The manifold name goes there, the point at which it's a tangent space goes there, and the T stands for tangent space. So x is an element of the tangent space is always written like that. Very frequently, the manifold is given the letter M, and you'll see TPM usually. But it doesn't really matter. The TP is the important part. It's the tangent space at the point P. Okay, and so once we have any element of the tangent space is now a vector, right? So this is now a vector because it's the element of a vector space, which is what this tangent space is. So any vector can be expressed in terms of components, just like we always do. And those components will look like this. Now, because it's a tangent space at P, you really do need to indicate that with this P here, right? But we understand that it really is this thing here that we're after, that this is the true representative when you do the full-on thing with all the charts, you know, and all of the the manifold X, and then you have your RD, and this is your chart U, and it's your mapping phi, and this is your inverse mapping phi inverse. Phi goes that way, phi inverse goes that way, and ultimately phi is defined by its coordinate functions, which in this case are x1, x2 through xd, and then you're taking derivatives of functions with respect to these coordinates. But of course, those functions like I've always said, go from the manifold to the real line. So the real function whose derivative you're taking is from our d to the real line, which is this function here, which is phi inverse composed with f, which is of course exactly what this would be. If you put an f here, it would land there. Okay. Anyway, that's sort of a 30-second recap of what we took 2 full lectures to do. But now we have our vector space, we have our basis vectors, and it looks like it's made full contact with what we did in the other lecture series, What is a Tensor? Well, what else did we do in the other series with What is a Tensor? Well, we talked about the cotangent space. And now we have to understand what the cotangent space is. So let's begin that. Let's begin that with a quick reminder of what the cotangent space actually is. And we won't go through the full formal development of the cotangent space, but we'll remind you it's the set of all maps from the tangent space to the real numbers. So if I say omega, if I use little omega, which is very typical, is an element of the cotangent space, then I know that omega is a map from the tangent space to the real numbers. And the set of all those maps is in the cotangent space. So I now need to be able to describe exactly how such a thing would operate. So how might we create such a thing? Well, let's think along these lines. If I have x as an element, well, let's see. X is also the name of my topological space, isn't it? So that's a collision already. Let me start with a different letter. Let's say y. Y is an element of the tangent space at the point P. So this tells us right away, we know that y is going to be, you can write y in terms of d by dx p, and then I probably need to show some chart mapping, right, because this is all charts. But I'm going to forego that. We're just going to work on one chart, so it's going to be unambiguous. I'm going to stay in one chart, so I'm not going to bother with the idea of putting the chart mapping symbol down there, and they usually don't. Now that we understand it, let's just agree that we're going to be on one chart for now. And if we have to add another chart or change coordinates, we'll come up with a new way of indicating it. In general relativity, they never indicate the chart specifically. What they do is they say this one coordinate system, and then they put a prime or a hat or a tilde for some other coordinate system, and that means the chart has changed. So we're going to start going back to that mode anyway, for now. So I'm going to get rid of this chart. So I'm going to get rid of this symbol for chart. We're not going to use that. We're just going to. The only reason we know it's a chart is we know these coordinate functions are associated with a chart, so we know there's a chart involved. But now we're just going to, instead of using the word chart, we'll start using the word coordinates, because we're going to get a little more back towards the way general relativity talks about this stuff. Okay. We know how. So this is how we would write down y. But we also know that when y hits a function, it gives us a real number, right? It produces a real number after it hits a function. And so one way of executing a map such as this, a map from the tangent space to R, is to lay down a function that every member can hit, and then it would give you R. So just as, so in some sense, just as we know that the vectors in the tangent space are associated with these curves, right? The ones that all go through the point, that is. I guess I can get them all to go through the point if I just turn them, right? So just as we know vectors are associated with curves, which have to be kind of provided in some way, these guys here are going to be associated with the functions, or I shouldn't call them functions, but the maps from the manifold to the real line. They're going to be associated with these C infinity guys. And each C infinity guide I can attach to the dual vector, just like I could attach the curves, in a sense, to the vectors. So the dual vectors are, the elements of the cotangent space are called dual vectors or covectors. And so each covector, I'm going to try to attribute, connect to a function in C infinity, and somehow I'm going to use that to create this map. So I'll create some symbols for it, and the symbol will be, well, just like we associated with the velocity last time. Let me change my coloring here. We would take the velocity and we wrote down the curve that it was a part of and the point it was at. Well, we're going to do something similar here. For the element, for the cotangent space, we're going to write the letter D, the function f will be next to it, and then we'll put the little p here to make sure we know that it's at p. And this is a bit parallel, right? We have the element of the vector space is v, the curve it's connected to is gamma, and the point is p. Here, the element of the cotangent space is going to be this combined thing, df, right? df is, well, it's sort of d, right? It's just, the d sort of fills the place of v, but the f is next to it. So this whole thing becomes the name of this object, this covector, and then we put the p down here. And this being a covector, it operates on a vector to give you a real number. That's what this means. This is the covector, omega, and it operates on a vector to give a real number. So actually now, for right now, since I want to be a little bit more specific, I could put df of p is a map. It's a covector. It's a map from the tangent space to the real number. So now how would that map work? How would that map function? How do we exploit this to get this map to work? And we just do the obvious thing. Well, the only thing. The obvious thing is, in this context, is the only thing you can do. df at the point P, that's the covector, operating on a vector, oops, sorry about that, operating on a vector, and our vector is y, right? That's going to be equal. The only way to produce a real number out of that is to have y operate on f, right? And that is a real number. So this operation, this covector operating on y, gives you the real number of y operating on the C infinity function from which this covector was constructed. And that's the definition. And with that definition, we can now create the set of all df's at P such that f is an element of the smooth functions on the manifold. And that is the cotangent space. And the cotangent space at P. And it is also a vector space. It is also a vector space. So that means that df at P plus dg, where g is another smooth function at P, there exists another function out there, h, say, that will always be the sum of those two. And so addition is defined on it, and a real number times df at P. There's also another function out there, dq at P, which is going to be equal to a real number times a. So this gives us our scalar. There's going to be a scalar multiplication rule, and there's a zero, and there's inverses, there's additive inverses. I'm not going to prove the vector space nature of all this stuff. It's actually a little bit easier for the cotangent space, I think, but otherwise it'll be another hour-long lecture. But this is a vector space. It's a cotangent space. It's a vector space, and it has the same dimensionality as the vector space, as the tangent space has. And just to be clear, to make the contact with what is a tensor lecture, the tangent space is the vector space. It's the underlying vector space, which we typically called V in those previous lectures. And the cotangent space is the dual space, which we called V star. So the cotangent space is the dual space of the vector space. And so this, and this is given a name. This cotangent space is given a name, and that's TPX with a star here, right? Because it's the dual space, so you always put the star. So TPX is the dual of TPX star is the dual of TPX. And it's just like the notation we used before. V is the dual, or V star is the dual of V. Well, likewise, V is the dual of V star because the double dual comes back to the original vector space, for what it's worth. But now we have both of them in position at every point in the manifold. Okay. So that is the core definition of the cotangent space. What about the basis vectors of the cotangent space? So we remember that there's the dual basis, right? The dual basis, which is still an arbitrary choice of ours, but we want it so that we're looking for, well, the way we phrased it last time is it was like this. The dual basis vectors mapping the basis vectors was supposed to equal the delta function. I guess I should put, one of these should be a nu, right? So e mu, e nu, or eta, how about that? Mu, eta, like that. And with that in mind, we are going to try to accomplish the same thing. I want to find the dual basis such that when I write down, well, first of all, I want to be able to write down a relationship like this, where this guy is d dxi at p, right? So that's the basis vectors of the tangent space. So I'm looking for the associated vectors in the cotangent space, say d omega, and there will be I of them, whatever they are, and I want it so that this gives me the there'll be I of them, but I have to give it a different index. This will be delta ji. I'm looking for these guys, and not too hard to find because they are just going to be the covectors associated with the coordinate functions. So the coordinates, remember, these are functions, right? Those are functions from the manifold to real numbers. xi is an element of C infinity on the manifold. So dxi is totally legit. Well, what happens when I take dxi and I operate it on dxj of p, right? This is a covector mapping a vector. This is the basis vector for the tangent space, and this is what I claim will be the dual basis vector. And this is easy to see because we know what the rule is. The rule for this mapping is the vector, or the element of the tangent space, operating on the function. And, well, what is that? Well, that's dxi dxj at p, which is delta I j. Now, notice how we don't have to retreat to the definition when we do this, right? When we do this, we don't have to go back to, okay, what does this thing actually mean? It means d of, say, d of j of xi composed with the chart inverse, right? Operating at phi of p, something like that. Right? We don't have to do that here. The beauty of this notation, the reason this notation was selected, is so you can actually very quickly get to this place. So although this is true, this is correct, it's not necessary to go back to it in this case. It was when we were trying to do this detailed stuff and understanding these charts very well, where, remember, phi equals x1, x2, dot, 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 xd, and these are the coordinate functions, right? And that's one of the coordinate functions. So we don't have to go back and do that anymore. We can trust that this notation works intuitively as partial derivatives would work. So this dxi, dxj, these coordinate functions, they're going to be the delta functions because they're independent, right? Xi is independent of xj unless j equals I, in which case its dependence is unity, right? Because it's the same function. So the dual basis vectors are these guys, the dxi of p. And once we have that, then any element of the dual space, any element of the cotangent space at x can be written omega equals omega I dxi at p, like that, where that's the component, real number, and that's the basis. And so now we have a way of writing the dual vectors, and we have a way of writing the vectors. xi d by dx I at p. Right, now, notice I've been dragging the p around, and in the What is Attention lectures, I didn't drag the p around because I built it out of one vector space, and then I stipulated, hey, I'm going to put one of these at every point on the manifold. But in this case, we actually started with those curves, so we had to locate a point to begin with, so I'm kind of dragging this p around. And we'll find a way to, I'll show you how we get rid of that p when we talk about vector fields, and we expand our manifold into something called the tangent bundle, which is a really interesting construction, and these little lines in the circle I'm drawing actually almost have nothing to do with what a tangent bundle actually is. We'll see how a tangent bundle is going to help us get rid of this notion of the p and broaden our understanding of all this. And so then the last thing perhaps to understand is that if we do change a chart, if we do change our coordinate system, right? So if omega is omega I dxi at p, like that, and we do change the coordinate system, and we go to a coordinate system with yi's. Now, when I say change a coordinate system, I'm talking about the whole formal thing, right? We have the point P, the chart gamma, the chart phi. Gamma is x1 to xd, phi is y1 to yd, and it's mapping it to a space like this, and the overlap region here is mapped to that region there, and the overlap region here is mapped to this region here, and we have these transition functions that go from these two regions and all that stuff. I'm breaking it down now into a coordinate transformation, and when those and the coordinate functions in those coordinate transformations will have those derivatives that we've discussed before when we just did the transformation of the vectors. And there we learned that the new component, xi, in one chart was equal to xi in the other chart dy, hold on, let me see, dy j dxi, like that, right? No, because the i's have to stay over. Hold on a second. It was, this would be a j, right? J. So yeah, because here's these are your dummy indices here, and then the j and the j match up. So this was the way the components of the vectors of the vectors transformed, or the component of the tangent vectors, the velocities, transformed. And if you do sort of a similar analysis, what you discover is that wi in, say, the phi chart is going to equal, well, let's see, I better stick with the notation. Wj in the phi chart is going to be Wj in the psi chart, and it's going to be the opposite. It's going to go dxi dy, dx, it's going to be wj, no, I don't know why this is so hard. This is obvious. There's only one way it can be. I don't know why I'm struggling with it. So it's, the down index will be j, then this up index will be I, and this down index will be I. The point is that this guy here is the opposite of, or the reciprocal of this guy there, and that's of course because dual vectors are dual vector components are covariant, and regular vector components are contravariant, and that's this reciprocal relationship. I'm just trying to make contact with what we've done in the What is a Tensor lecture. I'm not going to go through this proof. You saw how long it was to get this one. It's a very similar proof. Okay, so that allows us to now have this really good understanding that in our differential manifold, the manifold with its topology, with its atlas of compatible charts, in this differential manifold, at every point, P, Q, R, L, at all these points, we can create a tangent space, T, P of X, T, Q of X, T, L of X, T, Q of X, T, R of X. Likewise, a cotangent space at each of those points, T, P of X, T, cotangent Q of X, T, R of X. Every one of them gets both of these, right? And in addition to that, they will get all of the tensor product spaces that you can make out of these things. So a tensor product space construction can be made just like any other. If I guess the way you would have to write it down is you would write down TRX tensor product, TRX tensor product and then TR cotangent X tensor product and you could create PQ valence tensor product spaces, and you put all of those at every point. Every point can make one of those because they're all built out of the curves that go through those points, right? They're all built out of those curves, and they're built out of all these C infinity functions that all the C infinity functions that might send that point to the real numbers. So that you can construct all the tensor product spaces out of the tangent space and the cotangent space at each point on the manifold. So ultimately, the next step in our What is a Manifold, and I'm going to keep it into the What is a Manifold lecture series because we have to deal with the topological questions, so I don't want to bring it back into the other lecture series. But now we have to take this manifold, and the fact that these things exist at every point we really want to make a bigger manifold that includes all of these vector spaces as well. It includes the manifold itself, which we're going to call the base manifold, but we're going to make a bigger manifold that is the base manifold and every one of the tangent spaces. We'll start with the tangent space, and that's going to be called, we'll do this next time, the tangent bundle. The tangent bundle. And then we're going to create another big manifold that includes not the tangent spaces, but the cotangent spaces, and that'll be the cotangent bundle. Right? Cotangent bundle. And then we'll do it with the tensor product spaces, and that will be the tensor product space bundle, right? Each of these things that are attached to these points can be added to this underlying manifold and make something bigger, a bigger bundle. And that bundle will itself be a manifold with its own topology. And because it's a manifold, it'll be locally Euclidean. So just like this is locally Euclidean to RD, the new manifold will be Euclidean to, it turns out, it's going to go to R2D, right? The dimensionality of the whole manifold is going to double as soon as we do this plan of adding and enlarging the manifold. So that's kind of interesting. Okay, so that'll be for next time, and this was a shorter lecture, but that's because the last two were so long.